Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Great. So Eddie's going to give us a whiteboard talk.
Okay, can everybody hear me? Oh,
yeah, he's going to talk about a quantum approximate optimization algorithm.
Yes.
So take it away, Eddie.
Thank you. Can everyone hear me okay? My sound check okay?
Can we pull the door shut? I'm sorry.
Sure. Okay. So what I would like to talk about is an algorithm which I developed with my colleagues Sam Gutman and Jeffrey Goldstone over the last year, which is designed for finding approximate solutions to optimization of in combinatorial search. So my talk won't be that elementary. I assume we all know what combinatorial optimization is. I'm going to be interested in working on strings, Z, and I have a cost function, C of Z. This is an n-bit string, Z1 to Zn. I have a cost function, which is presumably a sum of clauses or local terms which act on a subset of the bits. And the cost I'm doing maximization here because when we talk about approximation ratios, it's important to talk about maximization because sometimes like the minimum of a cost function is 0. And then when you talk about ratios, it gets very confusing. So I'm always talking about maximization. And one thing that we are interested in is something called the approximation ratio. So if you have an algorithm, the algorithm will output C output, which means it finds a string that tries to do a good job, and you can divide that by the maximum, and that's called the approximation ratio. Okay, so that's something, if you have an algorithm, if you know, so it can be very difficult to estimate this sometimes because sometimes you don't know what the denominator is. If you have an algorithm, maybe you can figure out what the numerator is, but you don't always know what the denominator is. So that can be confusing, and I will talk about that in the context of the work we did, where sometimes we know the denominator and sometimes we don't. Okay? So I want to approach this with a quantum computer. So I'm going to make up a couple of primitives. One primitive I have is I call U of C gamma, and what that is e to the minus I gamma C. So this is just an operator which depends on the cost function, and what this does, this U C gamma, does to a string Z is it produces the phase e to the minus I gamma C of Z on the string Z, on a basis state. And the other primitive I have I'll call U. I'm going to define an operator B to be the sum of the sigma x's, where these over the n bits, and then U of B beta is equal to e to the minus I gamma B. And this is just rotates the qubits by an angle beta. And it's the same rotation on all of them. So we decided, so now the algorithm says, let's start in an initial state. And the initial state we're going to take is S, which you can think of as eigenstates, as the product of the eigenstates of the sigma x. Okay, because the sigma x eigenstates we usually call plus, but we can also write this as 1 over the square root of 2n, the sum on z, because this, we all know this, if you line up your spins in the x direction, you have the uniform superposition in the z direction of all possible strings. Are we comfy with that? Please stop and ask me questions. It's a very small group. If I say anything unclear. Okay? So this is a starting point of the algorithm. And this state, of course, it represents the uniform superposition of all possibilities. So if you made a measurement at this point in the computational basis, you would simply get a string z with probability 1 over 2 to the n, and therefore that corresponds to just randomly picking a string or randomly guessing. So the way the algorithm works is I'm going to define a state which is going to depend on a bunch of angles gamma 1 through gamma p, and beta 1 through beta p. And that's going to be u of, I'm just trying to remember whether the beta, yeah, the beta's on the outside. U of b beta p, u of c gamma p, so I nest these, and then I have u of b, that's a b, beta 1, u of c gamma 1 on s. So this is, so what I have now is this. I have these n, 2p angles. I have the set, this set of angles and this set of angles. These are angles because this has integer eigenvalues and the cost function has integer eigenvalues. So these things are just angles. If you wrap around, they come back. So this is the state which depends on 2p angles. And then what the whole algorithm is, create this state for a given set of angles and measure. And the goal is to optimize the state gamma 1 through gamma p. Let me write this as gamma vector and beta vector. The cost function gamma beta. The idea, you want to maximize that. So the algorithm is alternately call the cost function, the exponential of the cost function, do a rotation, call the cost function, rotate. And that's the whole algorithm. Now you'll notice that what I really want to do, though, is choose the best angles. I haven't said how to do that. But if I say to you now, the real way I want to run this is to find the best angles. You'll see that as I increase p, I can only do better. Because if I fix my angles, let's say for p equals 1, if I look at p equals 2, well, p equals 2 is the same as p equals 1 with the angle 0 for beta 2 equals 0, u of c gamma 2 equals 0, and then I have u of b beta 1, etc. You see, so as I increase p, and I do my how can I say it? At level p plus 1, I am doing an optimization which contains the optimization at the previous level. So I can only get better. Am I saying that clearly enough? Yeah. So it only improves. So that means that the approximation only can improve as you go to bigger depth. And we can also prove that as p goes to infinity, it's perfect. And the way you can see that happens is because if you think about I don't want to really prove that, but if you think about the adiabatic algorithm, if you have the adiabatic algorithm and you run it for infinite time, then you'll always get the optimal solution as long as you have a Hamiltonian which has a non-zero gap. And if you have a stochastic Hamiltonian, which this would correspond to, it'll always have a non-zero gap. And therefore, you can view this as p goes to infinity as a trotterization of the infinite time adiabatic algorithm. So I can prove that as p goes to infinity, this will work perfectly.
Are you making any assumption about convexity of the optimization or no?
No. No. When I said this, you mean that it only improves?
Yes.
No. Oh, no. All that's happening here is that if I look at p equals 2, I have 4 parameters. I need to optimize them. But the p equals 1 algorithm I can view as having 4 parameters with these two set to 0. So when I relax them, I can only improve the result. It has nothing to do with convexity. Okay? So now the question is, so let's see, as an example, let's look at some examples of this. And, you know, and as I go through an example, we might see how I'm going to show you how you can predetermine the angles in advance with classical preprocessing. Okay? But there's, so let's do an example. I want to first start with MaxCut. So MaxCut is the way I want to view MaxCut is I have a graph, whatever graph it is, you know, I don't know why I'm drawing it like this, but I have some graph. And the idea is I want to put on the vertices, I have bits, and what I want to do is my constraint says that the bits should disagree. That's how you get the cut. So I want to maximize I want to put down bits on the vertices, and I want to maximize the number of disagreements. It's like a coloring. It's like a two-coloring MaxCut. Okay? So in terms of if I turn in terms of the z's, my cost function C is minus the sum over the connections of ij. And let me write this as zi, zj as operators. But here I'm thinking of these as taking the value 1 and minus 1. So I want to maximize the number of this is the MaxCut function. Are we comfy with that, or that this is the MaxCut function? Okay. So I want to maximize that. Now let me tell you some results, which are sort of
This was with the constraint that I and J are neighbors?
Yes, this is what I mean. Well, the input is a graph, and this means I'm summing only over I and j in the graph, and then my cost function is minus zi, zj, because I maximize that if one is up and the other's down. Okay? So that's my goal, is to maximize that. So let's just understand, like, how hard is MaxCut? Well, one simple algorithm for MaxCut is to guess a random string. If you guess a random string for MaxCut, you will satisfy half the bonds. Because if you just think of this as, I mean, these are now random variables. So if I guess a random string, I satisfy half the bonds. Now, interestingly, and that's an algorithm, guess a random string. And interestingly, for a long time, that was the best algorithm for MaxCut. But then Gomans and Williamson came along and showed that there was a better algorithm for MaxCut, which I will not explain, but if you ask me to, it's very clever and cute. But anyway, so, and that algorithm, the Gomans-Williamson algorithm, takes the approximation ratio from a half to something like 0.878, ... which you can figure out what that is. It's the solution of a transcendental equation. Now, what's interesting about this, I mean, this is a little bit of an aside, but what's interesting about this is that that was not improved for a very long time. And people couldn't understand why they couldn't improve it. And then it was shown that if the unique games conjecture is true, if the unique games conjecture is true, then there is no polynomial time algorithm that can beat Gomans-Williamson. So it turns out there was a reason for it. Well, sort of a reason, a computer science type reason where you know that there are consequences of finding an algorithm. And so for MaxCut. So anyway, we decided to apply our algorithm to MaxCut, and I'll tell you what our result is, and then maybe I'll try to show you how we analyze it. When we do MaxCut, well, first of all, we made a restriction. We only looked at 3 regular graphs. So this means that graphs where every vertex every vertex has 3 edges. Now, that of course makes the problem easier because I've given you information. Okay, but then what we could do as at level p equals 1, Okay? At level p equals 1 on 3 regular graphs, we got a 0.69 approximation, dot, dot, dot. Now, of course, that is not as good as Gomans-Williamson, and in fact, for 3 regular graphs, you have to go beyond Gomans-Williamson for it to be significant, to 0.9 something. Because once I give you information, you know, how can I say it? When I say 0.878 is the unique games boundary, that's for all graphs. If I then tell you there's a restriction so that the graph is 3 regular, then it pushes the ratio up that you have to achieve to break the unique games boundary. So it's 0.9 something, I don't remember. But we did not achieve that. But we did improve on guessing. And in that sense, I think it was significant because it was an improvement on random guessing. And of course, had Gomans-Williamson not existed, then the quantum algorithm would have been, you know, much more interesting. But it does exist. So, but it is an improvement on random guessing. But I'd like to say one more thing about MaxCut. Another example we did is the ring. And so we have a ring, and I'm looking for the maximum cut on the ring. This is a 2 regular graph. And what's the maximum cut on the ring? It's 1 minus 1, 1 minus 1, 1 minus 1. And if it's even, you know, there's not even a defect. So it's very easy to solve. But what we could show is that our approximation ratio for this problem is 2p plus 1 over 2p plus 2. Now, so that has the feature that I said, that as p increases, it gets perfect. Now, but I want to say something about this. Suppose p is 1. Then we get a 3/4 approximation. Now, so what happens in this algorithm, you have to set the angles, and at p equals 1, you're going to, I mean, maybe I should have said what the algorithm is. Hold it. The algorithm is pick angles, create this state, and measure in the z basis. I should have said that. Yeah, okay, measure. So what happens, so if I go to p equals 1, I choose my angles properly for this thing, and I measure, I get a 3/4 approximation. But what I want to point out is that every string I measure satisfies 3/4 of the bonds. It's not true that I'm finding this with probability 3/4. Okay? So this algorithm, it is not working by producing a certain probability on the best configuration. It's working by producing only strings which meet that approximation ratio.
Well, on average, no? There will be some small variance, but...
The small variance, yeah, I mean, yeah, but I mean, when I make statements like that, I mean, as the number of clauses goes to infinity, you know, I could make it more precise. I could say exactly what I mean by that. Yes, but I mean, yes, of course, there's a statistical distribution. You know, there's a statistical distribution, but if you ask at p equals 1, what is the probability of getting this, which is the perfect thing, it's exponentially small. It's exponentially small. So I think that's a very interesting feature about this algorithm. It is not I mean, it's working to really produce approximations. And in that sense, it's different. I mean, you know, if you look at the quantum adiabatic algorithm, you could also say, well, maybe if I run it and I don't get the best solution, you know, then I'm still probably going to get a good one. And you could run the adiabatic algorithm as an approximate optimizer. And I don't really know. Of course, it can't analyze the performance of the quantum adiabatic algorithm for finding the best state, much less the approximate states. So I would say that the significance of these results are that we have the tools to actually analyze the algorithm on all instances of certain satisfied combinatorial optimization problems. Okay. Now, maybe okay. instead of telling you, maybe it's better to just tell stories and not show formulas. So let me tell you the next result, which has to do with another problem, III Lin 2. And then I can maybe go back and show you a little more detail. Is that okay? Yeah.
Clarification.
Yeah. Yeah.
To instantiate the algorithm, you must specify the angles. So that step, is that dependent on the instance? So you got your 3 regular graph. Now you choose the angles depending on that graph? Or do you do that independent of all the graphs?
Great. Okay, yeah. In this case, if for any fixed P, there is an efficient classical algorithm which will allow you to find the best angles for every instance. Now, when I say efficient, it's doubly exponential in P. So quickly as P gets big, it gets very, very hard, but it's not, it's efficient in N. It's not, it's polynomial in N. So, so you can classically preprocess. In other words, if I give you any instance of max3 sat, MaxCut, excuse me, of MaxCut, for example, I can tell you what the best angles are for a given graph. Mm-hmm. I can show you the best angles for a given graph. Now, some of the things, when I show you for III Lin 2, I'm going to pick universal angles to get the results we get. Now, this brings up another point about this algorithm. There's another way to run it. Instead of one thing you can do is you can go home and calculate the best angles by doing what gets to be quickly a very complicated computation. But for MaxCut at p equals 1, I could do this on my computer. And this number comes from a computer doing some math. And doing some, arithmetic, not math, arithmetic. Although, it's because we had to that's the worst case. You have, and also we estimated the denominator here. We got the denominator also. But what am I trying to say? Oh, yes, there's another way you could run the algorithm, which is this. Input a bunch of angles, and then run the quantum computer and get the string out and measure the cost function. Then pick another set of angles, measure the string, and get the cost function. And then you could have a meta routine, which is optimizing the angles, making calls to the quantum computer to get the value of the cost function. So that is a way you could run this. And I think if P gets large, like if you go to P as 20, probably that's what you would want to do, unless you know in advance how to pick the angles. So, and that's going to be case by case. We're going to have to think about that. But yeah, okay, so let me just say one thing about that. You see, the fact that one of the ways that you could run this algorithm is to pick angles and then make calls, and then pick another set of angle, make a call, pick another set of angles, make a call, and try to optimize. That means that if you have control error, it may not matter if it's reproducible. So, for example, so for example, suppose you think you're doing this. You're telling the quantum computer, I'm putting in an angle beta, execute this rotation on all the qubits by an angle beta. And it does it, and it outputs something. And as a function of beta, suppose that, the cost function looks like this, and you're trying to optimize. Now, suppose instead it's not doing that. It's putting in e to the minus I beta plus, 0.02 b. It's making a mistake. But when you do the calls, as long as this is reproduced every time, and you're optimizing, you don't care that the quantum machine is not exactly doing what you want. All you care about is that it's reproducibly giving you an answer. So I think this algorithm is very robust against control error when you run it in the mode of optimizing by making calls to the quantum computer, which I think is significant, because one of the things I want to do is I want to advocate that people start thinking about running this algorithm on a small quantum computer, because I think it has, well, maybe I shouldn't go on that. Well, yeah, I'll come back to that. But I mean, that's one of my goals here, is to try to talk to the Microsoft people about thinking about implementing this either through simulation or in their vision of the near-term quantum computer, because this algorithm, we don't really know what its ultimate performance is. It gets better as you increase P. It gets harder to analyze by hand as you increase P, but it's very robust against control error, and it has very shallow circuit depth. So I think it could probably run it without error correction at the basic levels. And the reason you can see it has low circuit depth, okay, maybe I'll talk about that for a minute. See, let's suppose, let's go back to MaxCut. Then this cost function is this. But that's, you know, so look at this object. This is e to the minus I gamma, and let me write it then as the product over ij, zi, you know, zj. Maybe I have my sign wrong, plus then maybe. So you see, if I tell you in my graph bits 1 and 99 are connected, then I have to do a single phase rotation using bits 1 and 99, which is diagonal in the z basis. So I have pairwise. For MaxCut, I simply have pairwise diagonal unitaries. And I know, Christy, you've been writing papers about the implementation of diagonal unitaries. And this is a case where I think that it's very natural. So for example, here, if I gave you a graph, if I could implement this function, and then I can do single qubit rotations by an angle beta, I'm at level p equals 1. The circuit depth is very small. And already at p equals 1, we have reasonably interesting results. So maybe if you go to p equals 10, you'll get you'll see much increased performance. I don't know. But again, I know I'm preaching a little bit, but I think this thing has an inherent robustness against control error. I think it has very shallow circuit depth. It has very simple primitives, which are just 1 qubit rotations, and cost functions, which are local and diagonal in the z basis. And I think, if you just alternate these, you may be able to do it without error correction. Or at least you should try it without error correction. And that means that I think it might be a good thing to do with a small quantum computer in the near future. Unless you have something better to do with it. Okay. Is there a question? Al? Yeah. No. Oh.
Okay, Al and then Dave.
I'd just like to understand the distinction between your version of MaxCut and the traditional definition of the MaxCut problem in complexity theory.
It's the same thing.
Which is, you have a graph, and then you want to find a cut of the vertices that maximizes the number of edges between
the
two sides. But the MaxCut problem in traditional complexity theory has a problem that you cannot find an arbitrarily close approximation to it unless p equals np.
Right.
So are you implying that as you increase p here and get an exact solution, then you will have shown that p equals np?
Oh, I see what you're saying. No, because it may be that the p I need to achieve, it may be, I don't know. Well, first of all, I'd like to break the unique games boundary, but okay, you're saying to me, what about the p versus np boundary? But it may be that I need p to be exponentially big in n to achieve that. You see, for fixed n, I can show that as p goes to infinity, it's perfect.
So you're not saying that a quantum computer can solve NP-complete problems in polynomial time?
I am not saying that.
Okay, well, just check.
You may also need to do many iterations of this.
Yeah.
Ask some random angles and get an answer. ask some other angles and get.
Yeah, yeah.
That may be all.
Yeah. No, yeah. But again, I mean, the statement that I should have said more precisely is for fixed n in the limit as p goes to infinity, we achieve perfection. So, you know, p may need, in practice, that may mean that p has to grow exponentially in n. Yes.
So I don't think you have to preach too hard. We read the paper and then implemented this for quantum chemistry and quantum materials. And so we have a version. It turns out p between 4 and 6 is plenty to get chemical accuracy, which is what the quantum chemists care about.
Oh,
and
really?
in a variational technique, very few gates, as you said, the depth is very, very small. Matthias, you want to interrupt or you want to take it after? You want to interrupt? Okay. Let him take it.
Krista, what time do I go till? 10?
Small p for a very small problem.
I said, well,
Yes.
I said for small quantum computers.
Yeah.
We're doing 4
For a small problem, that's trivial, not for a big one, because you talked about.
Ground state of water, you can find, you know, the 1 and 2 plaquette Hubbard models in
great.
3 to 800 gate depth, and with enough accuracy to just show that you can solve the problem. No, it's not interesting from a quantum computer solving a problem I can't do very quickly on my laptop. Agree completely. But for first machines, for first just qubits that we can actually control, we have experimentalists now interested, and we're going to try over the next period of time to actually get this up and running physically on real qubits, not just in simulation. And I said Hubbard model. So
No.
they're just planar, nearest neighbor connected. And then we're also doing this for water, which is fully connected across, so 2 body terms across, in that case, 14 qubits. Sorry. You were going to continue?
Okay.
Next?
So okay. So so let me tell you about, since some people were interested and didn't come to my talk on Wednesday, let me tell you what our results are for another problem. III Lin 2. So this problem is the following. I have n variables, and I have m equations. And each equation is of this form. Let's say, so every equation, this is called max III Lin 2. Max III Lin 2, but it's the same as 3XOR SAT, but it doesn't matter. It's max III Lin 2. Let me tell you what these words mean. It's a maximization problem. Every equation has exactly 3 variables. So it might be Z1 plus Z2 plus Z3. Mod 2 is either 0 or 1. In other words, every equation involves 3 variables. And each of these equations is exactly in this form, of the form variable plus variable plus variable. Mod 2 is either a 0 or a 1. So the way you specify an instance is by specifying a set of triples and whether they sum to 0 or 1. Okay, now, this problem, deciding if there's a solution is in P, because you can just do linear algebra. So I'm not interested in the case when there's a solution. I'm interested in the case when there's no solution. And the task is to maximize the number of satisfied equations. And that's why it's called max III Lin 2. Does that make sense, my problem? Any question about what I'm doing? Okay, that's max III Lin 2. Now, it turns out that there's, again, a good strategy, which is guess. And if you guess a random string, you're going to satisfy half the equations. Because if you just guess a random string, you know, there are 8 possible values for Z1, Z2, and Z3, and 4 of them add to 0, and 4 of them add to 1. Okay, so you guess a random string, you satisfy half the equations. So it was known in the year 2000 that if you can satisfy, if you can get an approximation ratio of a half plus epsilon for any epsilon, if you could do that, if you could get an efficient algorithm that gets a half plus epsilon for any epsilon, then P equals NP. So that's pretty amazing that, you know, the slightest improvement on random guessing leads to, so, you know, this is a really difficult problem to approximate then. Okay? Now, but I'm now going to do something else, is I'm going to say, let each variable be in no more than D equations. That's called bounded occurrence. No variable is in more than D equations. Now I've given you something. And the fact that I've given you something is going to allow you to make a little progress. And what you can then, and then it was shown in I think about the same time that you could get a half plus constant over D approximation ratio. Okay, so you see, you say no variable is in more than D equations, then that was achievable by Hofstad around the same time. Okay? And then we applied our algorithm, this one here, at level p equals 1. And what we actually showed, this was in the fall, is that we could achieve a half plus constant over d to the 3/4 times the number of equations. So what that means is that we actually showed that every instance you could satisfy that many equations, because we showed that the quantum computer would output a string that satisfied that many equations. So that's not the same as an approximation ratio. An approximation ratio, you have a numerator, which is what your algorithm is doing, and a denominator, which is the best for that possible. But what we showed is that you get this many equations satisfied, and you needed the quantum computer to find the string. Okay? So then Scott blogged about this. But the key thing was, I think, for the classical computer scientists who had been looking at this problem, was that we showed that there exist solutions. And that, you know, when we wrote to Luca Trevisan and we said we have a half plus constant over d to the 3/4. He said, how do you estimate the denominator? We said, there's no denominator. It's a half plus constant over d to the 3/4 times the number of equations. And, you know, he was very surprised. That got him going. So then the classical computer scientists got together and they managed to get, for a classical algorithm, a half plus constant over d to the 1/2, again existential, times the number of equations. So the classical computer scientists got this. They put out that paper a couple of months ago. Oded Regev and Luca Trevisan and Boaz Barak and a bunch of other people, 10-authored paper. And Hofstad also has a paper on this, getting that. So then we went back to our quantum algorithm, and we looked at it more carefully, and we could do the following. We were able to get, at level p equals 1, a half plus 1 over 101 d to the 1/2 log d times the number of equations. So we are off by a log factor relative to the classical algorithm now. But on the other hand, if we look at typical cases, and let me tell you what I mean by typical. What I mean by typical is I specify the triples, but for every specification of the triples, every equation could add up to 0 or 1. So there are 2 to the m instances for every specification of triples, because everyone could be a 0 or 1. So if you specify the triples and then you average over that, you get what I'm about to show you, but it's also tight. It is very little spread. And what we get then is a half plus 1 over 2 square root of 3e d to the 1/2 times the number of equations. So our average case, or a typical case, is consistent with this. And I don't know whether that log d is there because of a weakness of our analysis or whether the quantum computer cannot do better. I don't know. But I don't actually have a case that requires this. I mean, almost every instance has this. Almost every instance we have this. But I don't know whether this is just a weakness of analysis or is really there. So anyway, I'm not looking at that now, because I'm just not. Now, but it is interesting for this problem that if you could get a half plus constant over d to the 1/2 a sufficiently large constant, then p equals np. So we're really still, we're approaching again the p versus np boundary. But again, I mean, I think it will be interesting if I can't analyze p equals 2 or p equals 3 to run it on a quantum computer and see what the quantum computer produces. So I guess my time is up. So I just won't say anything else.
Great. Thanks, Eddie.
Yeah.
Maybe one question. We had a couple questions during the talk. Okay, Andres.
So these last results you've described are for what can be efficiently obtained, how many equations you can satisfy in reasonable time. Is there anything stronger known about just the purely mathematical question of how many equations can be simultaneously satisfied if you don't have any time constraints, if you could search through all strings? What's the best you could, in principle, do?
Well, no, you see, I mean, how can I say it? See, in this result, we actually proved that the typical instances satisfy that many equations. See, our result is existential because what we did is we showed that the quantum computer will output a string that satisfies that many equations. That means that many equations are satisfiable.
But do you know that you couldn't get more?
Oh, no, I don't know you can't get more. No, that I don't know. No, that I don't know. No, but the algorithm that we run will not find more because it finds that a certain level of approximation, and that's it. Oh no, shit! I shouldn't have said that. Because if I optimized over the angles, I don't know whether I wouldn't push the number higher. What I should have said is this: if I fixed my angles, then I know that every string that I output will satisfy the same number of equations. Now, this is worst case. So, but if I ran the algorithm by every single instance finding the best angles, I might produce a lot more. Suppose I had something that's trivially satisfiable. Like every equation sums to 1. So then I just put down all 1s. I'm pretty sure, I have to think about this, that the quantum algorithm, I can find angles which do a lot better than that. I can get a lot closer to 1 than a half. I can. But I haven't, I can. Does that help a little bit? Yeah.
Great. Okay, let's thank Eddie one more time.
Okay, you're welcome.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.